Hey folks, welcome to the last video in your 10.4 lecture series, and in this video we're going to take a look at using Taylor series to approximate a definite integral. This is very similar to example number 4 in the last video. We're just doing it with a different function and different numbers to get a little bit more practice, okay? All right, let's get started. So we're going to use the Taylor series to approximate the following definite integral. Don't be scared of the decimals. Don't be scared of the natural log. We're going to do so much of the things that are the same as what we did in the previous example, okay? All right, we are going to start off by using our table number 1 and our substitution. All right, these are skills from 10.3 that I think are really helpful. So if you need to go back and visit 10.3 lecture videos, definitely do that, but we're building on that, okay? So we know that g of x is, if it was natural log of 1 plus x, then table 1 actually gives us that, that series. And that is x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus, all right, our alternating, so negative 1 to the n minus 1 over n times x to the n. Okay? Now, this is our function. It's really close to the one we want. Let's see what kind of substitution we can make. So if I swap out x for x squared, I'm going to get the function I'm interested in. So let's make that substitution. G of x squared equals natural log of 1 plus x squared. That means that everywhere there's an x, I'm going to want to stick some parentheses, and inside the parentheses, I'm going to put x squared. So x squared minus 1/2 x squared squared plus 1/3 x squared cubed minus 1/4 x squared to the 4th. And I would keep going until I got to negative 1 n to the 1 minus 1 over n times x to the 2n, right? Because it's x squared to the n, and I'm going to multiply those. Okay, well, let's clean this up a little bit, shall we? We get x squared minus 1/2 x to the 4th plus 1/3 x to the 6th minus 1/4 x to the 8th plus our general term x to the 2n. Okay? I like practicing writing the general term because that was something we really worked on in 10.1 and 10.2. And so being able to get to that point, like if you're struggling with how to write this part, go back to 10.1, go back to 10.2 and see if you can't make sense of that. Okay? All right. So I used my table and I did some substitution. Now I'm going to integrate. And I'm not going to worry about my bounds yet. That'll be in step 3 when I plug in my bounds. Okay? So my f of x equals the integral of natural log of 1 plus x squared dx, which is the same as saying the integral of, I'm going to be a little lazy here, this Taylor series approximation. Okay? All right, so I know that I'm approximating. Now, just like the last video, I'm going to take each term at a time, and I'm going to integrate each term. All right, so the integral of x to the 2 is x to the 3 over 3 minus, let's see, x to the 5th over 2 times 5 plus x to the 6th over 3 times 7. That's supposed to be a 7. Minus x to the 9th over 4 times 9. Okay, so write enough until you can figure out that pattern. And then we have our alternating signs. There is an n on the bottom, but there's also a 2n plus 1 because I'm adding 1 to the power that I have, okay? So this 2n plus 1 is because I'm taking my power and I'm bringing it down below, okay? And then I know that there's a plus c. Okay. Now we get to evaluate. All right, so the integral between 0 and 0.34 of this natural log of 1 plus x squared dx is equal to f of 0.34 minus f of 0, right? That's what it means when we're going to take this integral that we got from above, we're going to plug in the top bound, and then we're going to plug in the bottom bound. And remember in the last video, even though I wrote out c in both of them, the c's are going to cancel because there'll be a c here and a c here. C minus c gives us 0. And when I look, if I plug in a 0 here, every term is going to 0 out. So really the only thing I have to plug in is the 0.34. Okay? So remember to write it out. Don't type it all into the calculator. 0.34 to the third over 3 minus 0.34 to the fifth over 10 minus 0.34 to the seventh over 21 minus 0.34 to the ninth over 36. And let's see how many of these terms we actually need. Okay, we don't want to write more than we have to, but I like to write at least 3 to 4 to give myself an idea of what's happening. And now we're going to take each term at a time and we're going to plug that into our calculator. And this is supposed to be a plus. My apologies, that's a plus. Okay, so when I take this and put it into the calculator, I get 0.013101. Okay, that's this first term. Then minus 0.000454. That's the second term. Plus the third term is going to give me 0.0000250011. Okay, well, let's go back because this seems like a lot of zeros. Let's go back and see what our maximum allowable error is. And the maximum allowable error is 10 to the negative 4. And when I type that into my calculator, that's the same as 0.0001. So I can stop writing my terms as soon as I'm done with 0.0001. Like I found something smaller than that. And I think we have, right? This is not smaller, this is not smaller, but this one is smaller. So what does that tell us? It tells us that we just need the first two terms to get our estimate. And this last term is how much our estimate will be off by, like our error, okay? All right, so our estimate, we add those together, we get 0.0126, and that is our approximation of this, or this definite integral, okay? So let me get that all on one page for you. There it is, almost. All right, let me know if you have any questions.